Hi. Come on. Come on in. Thank you. I'm Cliff Click, and if I can figure out which way the clicker goes, there it goes. So, in case you haven't seen me talk or seen me in action before, I've been a long-time startup guy. I've been CTO at a whole lot of companies. I've been writing code for more than 45 years, more than 40 years writing compilers. My first compiler was when I was 15. Many years doing many things, OSs, device drivers, distributed computation, HPC. Long time on HotSpot, both in and out of Sun and Azul systems, low latency GC, custom Java hardware. Last 10 years, a whole lot of machine learning, tool building, and applications. Lots of patents, lots and lots of public talks. So I'm going to roll the clock back a little bit. It was 1997, and Sun was doing this cool thing called Java, and they were intending it to run everywhere and run fast and run well. And at that time, there were plenty of ahead-of-time compilers. There was no distinction at that point. It was only ahead-of-time compilers. They were very slow to generate code, but they generated very good code. And the machines were much slower than they are now, and so the good code was interesting because it made your programs run acceptably faster. There were a lot of interpreted languages, like Python, floating around. There were some blended languages that mixed code generation and interpretation, but typically only with template-style code generation, so a little bit faster than interpreting, a lot slower than a static compiler. But as part of my PhD work, I figured out how to do a fast optimizing compiler. And that was what I wanted to do at Sun, and that was what I was hired to do. So heavy emphasis on fast generating of code, but also pretty good code. So fast on code meant you have an IR that is small. Why? Because if the IR fits in your L2 cache, or it doesn't fit in your L2 cache, you're 10 times slower or not. So you need to keep it small. Now, small does not mean simple. It can be very subtle, but it is going to be tiny. And now it's 22 years later. And I left Sun, in 2002. It's a long time ago. So my knowledge is dated. Sorry. I've looked at the code recently. I've talked to the maintainers and people who work on OpenJDK for a long time. And it is my belief that my knowledge is correct and up to date. But it might be wrong, and that's just, I've not been coding on the OpenJDK or at Oracle for, 15 years, 17 years, a long time. I will say that the Opto directory was the name that I picked when I was a grad student at Rice for my new cool optimizer. That was what I brought to Sun when I joined Sun in '97. So this is a compiler talk. And there are a lot of compiler jargon words floating around in it, like intermediate representation, and SSA form, and graph rewrite rules, and optimization passes like dead code elimination, and constant propagation, and global value numbering, which is a form of common sub-expression elimination, portable code generation, machine code, graph calling, register allocators. This is a hardcore compiler talk, and I'm not going to make any apologies about it. I'm going to use a lot of jargon, which is fairly specific to compilers, some of which I explain in later slides, and some of which you can read about elsewhere. So in the upper right corner, here's a resource, Engineering Compiler. Keith Cooper was my advisor, a nice, generic, good compiler book. This talk is about the C2 design philosophy, which is targeted at people who are hacking C2, or trying to understand it in more detail, or hacking compilers like C2. In the lower right corner, there's a nice resource for a high-level overview of what the compiler is and what's in it. I'm going to go into a lot of details in design philosophy of compilers. And it starts with the IR, which I came up with the word sea of nodes when I was a grad student at Rice. In this IR, it's always SSA form, even during final code scheduling and register allocation, and that's very unusual in that era. The IR is represented as nodes with edges, which makes it a graph, and it needs to be fast, so it needs to be small. So there's very limited data in the nodes, and we'll get more on that in a second. The edges are direct pointers, More on those also in a few slides. So that means they're unlabeled. So it's a very simple graph. The nodes have a label, it's like a plus or a call or a divide, and the edges just point from the use to the def. Data and control are in the same graph. Data is decoupled from the control flow graph in a funny way I'll show you in a minute, and kind of floats around. But there's one graph for both data and control, so it's a blended control flow, data flow graph. It's strongly typed. The typing system's somewhat more precise than Java. It lets me represent things that you cannot represent in Java. And that's because what the compiler wants to optimize is everything that Java can do, plus things that programmers intend by the way they stylistically write Java code. And so there are things that I understand that you can't say in Java directly in the typing system, but you say in Java by the action of what you code. And then the compiler is loosely coupled to the JVM runtime, and I'll not really hardly touch on that at all. You can have multiple compiler threads running in parallel, and this is common on a modern server where you have lots and lots of spare threads that you'll have multiple JITs, especially at startup time when there's lots of things to JIT. Okay, here is an eye chart of a sea of nodes. And we're going to break it down over the next couple slides. So this is program semantics as a single unified graph, as opposed to a two-layer control flow graph with basic blocks. On the left, I have a standard control flow graph with basic blocks. On the right, or in the middle, I guess, I have a sea of nodes. So you can see on the left, I'm in SSA form already because variable I has been assigned with a phi function on the start of the middle block, and there's I0 and I1 and I2, and however many names you need to get a statically single assignment to each unique variable. In the middle, you can see something that looks kind of related to what's on the left. So there's an adds and multiplies and constants 10 and 2 and less than and things like that. There's a phi. All in the green nodes, it looks like data. The yellow is something to do with control, with region and if and a return. And let's go, and I'll go break it down in a second. I'm going to mention there's some resources on the right. The resources slide at the end, and the slides are available online, so you can get all these resources. You don't have to picture it here. So there's more discussion to be available offline, but let's go break it down. So starting with control, there is an embedded control flow graph in the sea of nodes. I did briefly toy with a program dependence graph, which is not any control flow graph, but I decided it was too much new technology, 25 years ago when I started this, and so I backed away from using a PDG, and I just went through a CFG, which is embedded, but it does not have any traditional basic blocks. So I have a start, which is where the program or the compilation unit begins. There's regions for merging control that has been split somewhere else. There's an if for splitting control. You can see the yellows coming out of the if. There's 2, so it has split from 1 coming in, 2 going out. There's a call, which is serialized. There's this funny C proj I'm going to cover in a minute. And so the control on a call just comes in and goes out, and it forces it to be serialized. And so there is a CFG that can be picked out directly, but there's no basic blocks in here. Why are there no basic blocks? Because most of the things I do don't care about basic block boundaries. And so I don't want to continuously massage them. In fact, during the optimizer, which we'll cover here in a minute, I will continuously reshape the graph with control and data intermingling arbitrarily, and not ever care about a basic block boundary. And so I don't want to have to make a step to manage and say, make it, break it, make it, break it. Control flow, the basic blocks come and go sort of obliviously to what I'm doing with the graph, and so I don't pay any attention to them, and I don't need to, and that's sort of the beauty and the simplicity of optimizing here. I do mention the start here is that also the end for convenience, and I can walk the graph in either direction. Here's the data side of things. And it looks much closer to a data flow graph than the control flow graph looks like control flow. There's constants, there's basic math, there's phi functions, same as SSA always has phi functions. There's no variable names anymore. Variable names exist when I build the SSA form from bytecodes. Right, so this is a language for optimizing, people say Java. No, it's a language for optimizing Java bytecodes. This is an IR for optimizing Java bytecodes. So I read Java bytecodes and build the SSA form in the very beginning in one pass, pass and a half. And at that time, there was a mapping from names to nodes, but that's forgotten when I'm actually doing the optimization, when I'm actually working on the optimized form. The control and data are blended. So the call here produces out a control, but it also produces out from that green projection a data value, a return value from the call. Turns out it also produces a state of memory, which is represented as a node in the graph. Produces out the class of exceptions that you can throw. Also comes out as a piece of graph IR. The if here takes in a data value to gate which way the if goes, the false or the true. And it has two control edges out, a false and a true. The return here obviously takes in a data value, which is the return value from the function. Turns out the call also takes in data values for arguments, as well as control to force the threading. Edges, only edges order operations. So I'm showing def use edges. The actual implementation has only use def edges, because that's the raw pointer from the use to the def. And that's your only ordering, and that's your total semantics. So values have no place. Computations, like the green things, have no place in the IR, no home location, if you will, no basic block. And that means that I cannot care where they land when I do optimizations on them. And that's crucial for simplicity. I cannot even think about what basic block is involved because there is no basic block to be involved. Which means that they might as well be here instead of, here. I can't actually tell the difference. But this is the version of them where I've graphically shown you they're outside of the loop. And we can see the loop structure has a very simple add of a fee of whatever came in from the console, less than 10 or whatever. That's the IR in a sort of high-level nutshell. So the compiler uses the IR in a bunch of passes, and I'm showing wave after wave after wave. This is an abbreviated version of the main passes. So there's build it in a pass and a half from bytecodes, which includes inlining and people optimizations. I'll talk a lot more about them in a minute. There's a major optimization pass called iter for iteration. Repeating people optimizations until you're done. And the people optimizations do a lot of things, including dead code elimination, constant propagation, common sub-expression elimination, load after store, store after load, dead if, dead this, add of zero, address math, reassociation. There are hundreds and hundreds of optimizations done by the peepholes, and that is actually the main optimizations that come out of the compiler. Sort of the classic, you think of optimization, iter and peepholes do almost all the heavy lifting. With the exception of loops, your performance comes from iter. Iter is also guaranteed linear in the size of the compilation unit, no matter how many times I call it. So it is called after every other kind of optimization takes place, like any of the loop ops. I always call iter every time, and the sum of all iter calls will be linear in the size of the program, so it's very convenient to use and very fast. Global constant propagation, loop optimizations, loop unrolling, range check elimination, things like that. Eventually I get down to global code motion. That is a global latency aware, frequency aware scheduler. At that point, the graph becomes fragile, because at that point you now have basic blocks and things are placed, and I cannot anymore change the graph without thinking about basic blocks. Code has a place, and I have to deal with that place. So the typical answer is I don't. I get all those optimizations done first. Once they're in a basic block, I'm headed to the end run. I'm going to do code generation, convert ideal adds into x86 add instructions with machine code representations, do a register allocation, and then you install the code in the JVM and away it runs. So let's talk about nodes, because this is part of being small and fast and convenient to optimize on. So, HotSpot's written in C++. So C2 is a big C++ compiler written in C++. There's a vtable, which is your opcode semantics. There are about 35 virtual calls. There's the name, the people optimizations that are allowed, the constant propagation, a bunch of debug prints, and a whole lot of other things that come one after another. There's a limited amount of RTTI because there are certain questions you ask a lot, and you ask them, You would normally ask them with a vcall, but the cost of a vcall on a C, C++, is relatively expensive, but these are all Boolean questions based on the class, so they just turn to a bit vector. So the RTTI is a short with a pile of bits that you query a bit that's structured as if it was a vcall, but implemented as a load bit mask for speed. Otherwise, you have edge arrays for the input edges and the output edges. So the basic node is a vtable. It has the RTTI word. It has a pointer to the array base for the input edges and a length, and a pointer to the array base for the output edges and a length, and that's it. And that's crucial for speed, because you're going to have many thousands of these nodes, and if it fits in your L2, like I said, if it fits in your L2, you're going to be 10 times faster than if it does not fit in your L2. Okay, use step edges, they're raw C pointers for speed, as I mentioned. They have an ordering, and A divided by B is not B divided by A, so it matters what the order is on the edges. Null is allowed here. It's common in slot 0 because that's been reserved to have a control dependency if you do. Most nodes don't. The explicit def use edges come a little bit later, and they're unordered, just a list of nodes that represent uses. There's a whole lot of macros for iterating over the uses as a work list, as a drain them until there are no more uses, as a add them and the iterator knows that things will get added and it'll make sure to visit them, or things will get deleted and it will handle that as it goes. So there's a bunch of iterators depending on how you want to treat the output edges. Like there's no concurrent modification exception. Instead, there is, what are the semantics you want when you're doing concurrent modification? Because damn well, you are very much doing concurrent modification. Okay? Peepholes. These are basically graph rewrite rules, and in which you inspect a local region of the graph, and you replace inside the region with a semantically equivalent piece of graph that's somehow better. And there's no change outside of that area, so your nice neighbors in the graph are unaware of the change. And when I say, what is local, I mean, if you put the graph as a planar representation on a piece of paper and you drew a loop around a section where you crossed edges but you never sliced the node, nodes are either in or out. And if they're in, they're local, and if they're out, they're not. And if they're right on the edge where you have an edge that is sliced of your circle, then they're a neighbor. Most of these areas are rooted at a single node, which has a virtual call, what's called ideal, that does an inspection of what it declares to be its local area and makes the change if it thinks there's something beneficial, and flags saying, hey, I made a change. There are literally hundreds of these rules. Most of them are trivially obvious. So if I go to like addnode.cpp in the opto directory in C2, I'll see adds do things for +0 for ints and floats, and ands and ors do the equivalent thing for multiple by 1 and the like. And if I have stacked adds that happen all the time in array addressing math, they'll reassociate constants near each other so I can constant fold, and of course it does constant folding as well. And there's reassociating for things that look like loop iterator counters, and reassociation for a bunch of other rules. You'll see dozens in add, the same dozens for multiply, a bunch dozens for load, bunch dozens for store, and pretty soon you have hundreds of such rules. Iter, as I said, was a major optimization pass. I call it pass because it's actually called many times, but effectively the cost is one pass. You pull a node from a work list, you do peepholes if possible, you do a bunch of things that are common to all nodes, including constant prop, global value numbering, common sub-expression elimination, dead code elimination, and then you push neighbors. If you made a change, you push neighbors back onto the work list, and you repeat until the work list runs dry. And it turns out that if you've set your peepholes reasonably, it will run in linear time. It will monotonically come to the same graph representation, irregardless of the order you visit things on the work list. And it will get all your easy or your junk stuff. It'll make your code clean, neat, tidy, looking like a handwritten machine code writer would do when he was trying to do a good job, right? And like I said, it's fast. It's called all over the compiler. It is the thing you do when you're done doing something else that was sort of major. Edges. Let's talk about edges. What are we doing here? Yeah. Edges are direct pointers, as I mentioned, for speed. And they're plain C pointers. And so they can't carry any labels. Now, why do I want to label edges? Well, it turns out I don't need to label the useDef edges because they're already ordered by the output where they are in the nodes for their inputs, I guess. And that's where your meaning comes from. That's A divided by B versus B divided by A. Or if you're load instruction, you have a memory and an address. And if you're store, you have a memory, an address, and a value. And these are the order, and they're in a particular order, and that matters. Fine. Sometimes, though, it matters what the output looks like. So an if has a true and a false control. And a call produces a control out, and it produces a return value. It produces a state of memory, and it produces a bunch of exceptions. So if I have a direct pointer to the call node, I can't tell which of those outputs I intend. So I need to label that edge. And the way I do that is I declare a call to produce a tuple of results, produces a collection. 1, 2, 3, 4, 5. It's a known length, fixed count, whatever it happens to be. Calls produce a different count than ifs. Fine. And there are other ones than call and if. And then I have a projection to take a slice out of a tuple. And that's where I see the word, you see proj, short for projection. And the projections have a number inside, an index 0, 1, 2, 3, 4. It says which slice they're taking out of the tuple. And effectively, that lets me label an edge. But I only end up labeling the edges where I need to label the edges and not everywhere. And so that gives me the 95% case being fast, and the 5% case pays the one indirection cost to get to the call by hopping through the label that tells which piece of the call they are actually interested in. Okay, let's talk about types for a little bit here. In the graph IR, the graph represents, if you will, as an analog, the paragraph, the sentences that you make up your program, where the types would be like the words and the characters. It's what you can talk about. And if you can't talk about a thing, if you can't represent it as a type, you can't do any analysis or optimization on it at all. So types are the things that the compiler can reason about. They are represented mathematically as a set of values, including all the integers as a set, or all the floats, or pi, or no, or some class, or whatever. Every node has a type, including control as a type for things like regions and the control out of a call and in and out of ifs. Types are obviously used in like constant propagation because you might have a constant like 0 on an add, which, you know, the constant 0 is a type. But they're also used for class hierarchy analysis. That's CHA. And class hierarchy analysis is where I look at the set of classes that are possible here, and maybe more specifically on the set of functions that are implemented by the set of classes that can happen for this particular node. And I can often discover that there's only one function call possible in the set of classes, and if I can get a more precise type there, that I can narrow the set of classes down. And if I get it down to one function implementation for that call, then I can now make it a static call in inline, right? So CHA is a crucial performance optimization because it enables inlining, and it's done by looking at the type of the this pointer at a call. But it's also used for dead tests, for switches, for range check elimination, for upcasting, in many, many, many places. Types are what the compiler reasons about when it does real optimization. So, what are the kinds of things? All the integer sizes, byte, short, char, int, long. Arbitrary ranges are the same, which happens a lot in range check for counted loops of fixed known iteration, but also a lot of people screw around with small count things for Boolean tests or 0, 1, 2, 3, 4 kind of enums. It happens all the time. So small range counts are allowed. Float constants, floating double-sized things. Tuples, arrays, instance objects, the memory state, these are all like the contents of a Java object that I know exactly will have exact values for all the fields as well. The equivalence class for aliasing, this would be the set of things that might possibly alias to the same memory location where I get confused about pointers. What are the rules and where I get confused about pointers? That's part of the type system. And pointers themselves have a couple different variations. There's raw, which is unsafe, right? There's object-oriented pointer, OOP, which is a garbage-collected pointer. These are instances, Java arrays, capital K class objects, which would be the reflective version of a Java class object kind of thing. Classes can be both exact and inexact, by which I mean in this little class type hierarchy, hash map has some children classes and some parent classes, and I can say that this thing is hash map and below, or exactly hash map and nothing below. But I can distinguish those cases, and for every possible type in the system. So it does everything that Java types do, plus it has some more precision in key places where it matters, like null or not null. I didn't show this, but I can tell you a pointer's null or not as a separate aspect of the typing system. The types define a lattice. And at the bottom I say, hey, go to Wikipedia and read up on lattices if you don't know. But if you're screwing around in C2 in a major way, go read up on lattices. It's a lattice that's defined by meet and dual, not by meet and join. Semantically equivalent. It's complete, complemented, bounded, mostly distributed lattice. So it kind of makes it a Boolean algebra except for the mostly distributed. Those concepts are key to being correct and fast. And they're not obvious as to why they're key to being correct and fast. So let me finish the slide, and I'll come back and visit them again here. So I have a lattice. What's a lattice? Well, here's a sample lattice in the top right corner for the constants, where I have things on the center line, -3, 2, 1, 0, 1, 2, 3. Those are constant values. I might say something is a constant 2, right, or a constant 0. What is bottom? Bottom says, I don't know what value it is. It's some integer, but it could be any of them. I don't know which one. And so I have to compute it the correct way. Whatever the programmer wrote to get that value, I have to go implement the same semantics and machine code to get that value. Top is the opposite of bottom. It's the constants, it's all the constants all the time. I can choose which one I want as convenient. Whereas bottom, I must compute, I have to honor what the programmer wrote. The top, I can choose any value I want. So they're on opposite ends of the spectrum, if you will. It's a little odd notion. So here's a same concept for strings, where I might have constant strings and null, but bottom is, it's some string, I don't know what kind of string it is. And top is, I can pick the string I want. That notion shows up in all the optimizations, where all the optimistic optimizations, we'll come to it in a little bit, where I'm going to start everything at top and fall, and there's a crucial property to get your code quality out. And then I extend that notion to everything else, not just ints or floats, but also Java instances, Java classes, capital K classes, everything has the same notion. So back around to my Boolean algebra here. Complete means if I compute a meet, I find the least common ancestor, the lowest thing that meets, that handles both left and the right. It means a pairwise operator that gives me something. Complete means I find something else in the lattice. I don't go outside my lattice. Complemented means I have an inverse for everything. Distributive means that I can do meet and join in either order, in any order. And the crucial property there is it doesn't matter what order I do things in. I will always get the same answer, which is now provably an optimal answer in all cases. Which means I can do a standard work list algorithm that just pulls and grabs in any order, and I guarantee you I'll give you the same answer when I'm done with the work list, no matter what order things happen in, and that gives me very simple implementation strategy. Pull from a work list, compute a type, repeat until you're done. Right? And you're guaranteed get the best answer, and guaranteed get a fast linear time answer. So, types. This is type HPP, CPP in the C2 opto directory. Type descriptions can get big. They represent a very complicated structure. So they're also immutable. So they are hash cons or intern. Go look it up if you don't know what that means. The reason to do hash consing is that when I'm done, I only have one instance of a particular type, even if it was large and complicated. Because I only have one instance, I can compare it with equal equals instead of dot equals. In fact, it is incorrect to use dot equals. It's asymptotically slower typically because you have to do a structural breakdown of the complicated types to do a comparison with dot equals until you're recursive, and then you're infinite in the structural check. So you must use equal equals after interning. But then it's one clock cycle on an x86. It's super fast, right? The other thing going on here is, of course, most types hit in the hash cons table. So the types are produced and thrown away millions of times, but only a few thousand ever show up in any particular compilation unit. So the ratio of make to keep is 1,000 to 1. And because I recycle them immediately in memory, they all live in your L1. I make one, I look at the hash cons, I get a hit 99.9%, I reclaim that memory, and I use it again for the next type. I'm going to look in the hash cons table. All hits in L1. It's one of the fast things we do. I guess the final thing here is just join is just, because it's symmetric, or complemented. You can dual the two inputs, do a meet, and then dual the output. That's the join. Is a, pi is a float 64 is done by meet equal the right-hand side. So this is crucial for both speed and quality of optimization because this is what I can talk about in the compiler. Pessimistic versus optimistic. Iter and the peepholes are all pessimistic. And what does that mean? It means the program begins correct and ends correct, and the peephole optimization preserves correctness, but it may make a change as it goes. Types throughout the program start at some value I got from the bytecodes, and I lift them over time in the lattice, literally up the lattice from bottom to constant to top maybe. It only goes to top if it goes dead. But at any point I can stop running iter and I have a correct program. GCP, its global constant propagation, is optimistic, not pessimistic. I initialize all my types to top. I mentioned I had to have top. Well, this is what it's for. Program's now not correct because type represents an ambiguous state. I don't understand what it means in the real world, but in a mathematical sense, it works out. Types now fall as I resolve conflicts. And they fall over time until I get stable, and I no longer need to fall. At that point, the program's now correct. GCP is monotonically better than iter. It strictly finds every constant iter finds, plus it generally finds more, generally a fair amount more. Every time you do anything in and around loops, not just with integers or floats, but especially with objects with types, GCP wins. It finds all kinds of nulls that you couldn't find before. It finds all kinds of precise types that you couldn't find before. So GCP is a powerful optimizer for discovering what you intended to write as opposed to what the compiler had to assume because of localized analysis. Okay, both iter and GCP use what's in the compiler called the value call. It's like the ideal call, but it's for doing type math. So what a value call on a node does, it's a vcall. What it does is it looks at your uStef edges, gets the types of your inputs, and computes a new type for this node based on types of its inputs, right? So if you have an add of a constant 2 and 3, he looks at the 2, looks at 3, he does the math for two constants, it says it's 5. But if he has an unknown bottom value and a 2, and he looks and he says bottom plus 2 is bottom, and he sticks at bottom and there's no change, right? So value call is used for both iter and GCP. In one, the types are strictly lifting, and the other types are strictly falling. And they don't, by the way, they touch, but they never go past because GCP wins there. So the value call has to be monotonic, which means an output will fall if and only if an input falls. There's another way to look at it. If all your old input types is a new input types, then an old output type will always be a new output type. Is a new output type. So funny little math. It's not hard to make happen, but if you fail to get this right, then GCP will not terminate. Okay, inlining. So how does this work? Some execution, we're going to start from the start here. Some execution triggers the compilation. You hit the 10,000 point limit. And at that point, the runtime hunts up the stack for a suitable method to begin compilation at. Why don't you start compiling at what hit the 10K limit? Because typically what hits the 10K limit first is a getter. So it's not a thing that you care really to compile. You want the getter to be compiled inside of something else, probably a couple loop nesting depths, and some other common shared code. So you hunt up the stack for some suitable point. And once you start there, you begin parsing bytecodes and building SSA, and as you come across invoke calls, you decide to inline or not at that time. And so you're basically hunting down stack for inlines as you parse bytecodes and build the IR. You use class hierarchy analysis, which is fed from the peepholes. Why can I feed peepholes while I'm parsing? It turns out peepholes are always conservatively correct. So peephole analysis runs while you have a partially parsed method, and you have more of the method to parse, but things you've parsed so far can totally run through the peepholes, which will totally clean out all the junk shit, pardon my French. And, sorry, Henry. And, you give you a sharper type, which will help you decide to inline or not. After that, you hit the inline heuristics, which are mostly small and hot. Always you inline the trigger method and things that lead up to the trigger method, and always inline intrinsics and unsafe and some trivial getters and setters, some really tight rules for the always. You exclude things that are already compiled and kind of big, or you'll have iCache blowout problems. I say iCache blowout, oh no, it's the compiler talk, I'm going to carry on here. So the decision's made at bytecode parse time. Or at least it was 20 years ago, and I tried hard to change it on and off throughout the years, and I don't know where it is now, but I suspect it hasn't moved very far from there. So it's too early, usually. You have limited, detailed optimizer knowledge. You got the peepholes, but you didn't get GCP, for instance. And you don't have in-depth frequency analysis yet. You get the counters come out, and they go right into the IR as performance metrics, but they're not available during the bytecode parse everywhere. So you don't necessarily get the precision you want. The constant arguments is another heuristic that says it's useful to inline this guy because all his inputs are null, for instance, and that almost always means that internally this method will hit a null pointer check and bail out. So I can inline it because it's probably going to die instantly and be no code, right? So it's free to inline. So you get some hit or miss on inlining, which we're going to compensate by very aggressive inlining. Now, at the time I did this thing, people who very aggressively inlined in the static compiler land typically blew out the register allocator. And there was a knee in the curve, a performance curve, where more inlining got you more performance until the allocator blew out and then you fell off the curve. And now you sucked really badly. And so it was dangerous to get too close to the knee because you might fall off. So you dialed back inlining that you never really got to the knee very often. It's very rare you'd hit the knee. And you left a lot of performance on the table because of fear of hitting the knee in the curve. So in one more slide, I got these maybe in a different order, we're going to talk about allocation. So before allocation, we do code motion. This is where I build a real CFG. I unwind the C part of the sea of nodes, and I put things back into basic blocks. This is a global latency-aware, frequency-aware scheduler. There's a paper that describes the algorithm down below. Basically, it's going to move code out of loops into low-frequency branches. Typically, Deoptimization paths are very, very low frequency. It does require anti-dependencies, which use the precise aliasing info we've gotten now after all our optimizations. And at this point, the IR becomes fragile. Code motion is a thing now. Up to this point, all my people optimizations were free to ignore location because there was no location notion. I couldn't even talk about it. Now I can not only talk about it, I have to pay attention to it, I have to deal with it. So the typical answer is I don't do any after code motion. I'm all done doing all your classic optimizations. Graph culling register allocator, probably the single slowest phase, probably the single most complicated phase, probably responsible for the greatest speed up across all codes. It certainly was the case when I left Sun, however long ago. And the reason being is that it's robust to over-inlining. Spill code costs are almost always cheaper than the equivalent cost you get if you failed to inline, but you had to pay a prologue and epilogue around a call costs. So as long as those two are equivalent, the only cost to too much inlining is you might eventually hit iCache blowout. Which means that C2 can crank up inlining without hitting performance knee. And that was not true of all the static compilers of that era. I tried, all the ones I ever looked at. I looked at a lot. The allocator deserves its own long talk, which I'm not going to do here. You get one slide, and we're going to roll on. Okay, so I'm going to roll through some Java-specific optimizations. And when I say Java-specific, what I really mean is no compiler up till Java cared about this stuff very much. So they didn't do a good job because they didn't need to. It didn't matter. So there are a lot of bytecode checks in Java that are baked in, come for the type safety in the language. For me, for C2, there's no difference between a user-written null check and a built-in bytecode null check. Literally no difference. There's performance counters. They both get them in the same kind of way. There's the same kind of compile optimizations, the same kind of implementation strategies that come out of that. So then I made the compiler robust to having huge counts of safety checks. In particular, 90% of your null checks get eliminated during bytecode parsing by people optimizations. Like a huge count of them just go away before they ever get out of bytecode parsing. This is actually a compile speed issue because the IR without doing peoples is 4 times larger coming out of bytecode parsing if you don't do the peoples then and do them later, which turns into a whole lot more slowdown later, because you eventually get rid of them all, but it takes a while. Much faster to get rid of them during parsing. Okay, fine. Once you've decided that you can't get rid of a null check, there are 2 strategies. One is a hardware check against a memory op. I just do a load against your pointer, and if it's null, I take a segv. And then the runtime catches the segv exception, does a table lookup, decides this particular address refers to a load that's doing a null check, and you're throwing a null pointer exception. And then it converts that into a Java null pointer exception. And 5% turn into an explicit branch, jump not equal, right? Compilers of that era just didn't deal with this problem, mostly because they didn't have to. If you were a C coder and you wrote a null pointer check, you wrote a null pointer fail, you took a segv and you died. You had a bug in your program, you had to fix it. Okay, well you fixed it by putting in a null check lazily as you found you had to go fix your bugs. And then you had a handful of null checks, and the compiler just put an explicit branch in because the user wrote a null check, and that's what it was going to do. And then that was it. There was no more null pointer handling. And if you hit a segv later, well, you crashed and burned with a segv fault. Okay, so Java turned those into null pointer exceptions, and at least now you get a nice handy stack trace as part of your crash. So some other optimizations for null checks. Here's one of them is called unzipping. And this would be a case where I test something for null, and I branch null and not null, and then I flow together, and a little bit later I test the same thing again. I loaded a field from this pointer, and I split, not a this, some other object. I loaded from a pointer, and I loaded another field, and I loaded another field. I'm testing the same pointer over and over and over again for null. So, in the left, I see split and join, split and join, split and join. In the middle, I see the unzipping, where I've replicated C and F. And in many of these cases, C and F are quite small, maybe even empty, and the replication's basically free, and I have these nice straight lines to optimize through, do other kinds of optimization, including common sub-expressions are now common because there's no control flow in the middle, and scheduler can rearrange things better. But it might also be the case that the test hardly ever fails. So if it's never failed yet, I can just cut it off and say, go to the interpreter if it ever fails. And now that I don't have to deal with that path, then I have one straight line piece of code, no replication, and in fact, no merge pointed I either. This is a very common strategy that shows up all the time that people don't realize the unzipping operation happens. CHA, class hierarchy analysis. Turns out that even though it's mostly done early, it mostly does a really good job. About 90% of your standard Java calls are determined statically at that time, at bytecode parse time, which enables them to be inlined. Maybe you have to have a guard test if you have a frequency and you have maybe a couple choices, but there's one high frequency choice. If you can't get it with CHA, you use an inline cache. And an inline cache has another interesting bimodal distribution. 90% of inline caches hit. What's inline cache? Let me tell you, inline cache is it's a one entry cache that's embedded directly into the code. There is a key and a value. It's a standard cache key value. The key is the class you expect. The value is a static call to the static method you're going to go to if you got the correct class. So they're directly embedded in the machine code as a compare of the object's class against the expected class. So the class pointer you're looking for is a hardware instruction as a constant bits. And then the method you want to go to is put in as a call instruction, literally hardware call instruction, to the JITted version of the code that you want to go to. So on a hit, it's a load compare branch. You got the correct class. That's one clock cycle on an x86. Second one, static call to a known target. It's 2 clocks to do a virtual call for roughly 90% of the 10% using inline caches. The remaining calls are actually megamorphic. They actually go to multiple targets. And there you have to do the hard math, which is a load, 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 jump register. About 30 clocks on a modern processor still. The loads are dependent, so they can't be prefetched through. If they're in your L1 cache, which is not commonly the case for some of them, they're 3 clocks, so there's a minimum of 9 getting to the jump. And if the jump register hits in your branch target buffer, it's still several clocks to do that. So it might be as cheap as a dozen clocks. But if you miss in your L1, which is common for the header of many objects, then you're going to be dozen for L2 or hundreds if you're off to L3. It's not typically very fast to do a vcall. It's not 2 clocks. Fine. Range check elimination, I was going to put a big slide in here, and I decided I was going to be both out of time and out of slides, so I didn't. So you only get the high-level overview, sorry. So, range checks, they're only necessary at this time. At that time, they're only necessary for Java because C didn't do any range checks. You just had, buffer overrun and you died, and that was all these security hacks were done by buffer overruns. Identify bounded loops. Turns out they have a very classic pattern in the IR. Very, very simple, very clear pattern in the IR. Now that you've done iter to clean up all the junk, the pattern is very obvious what an induction variable looks like and what a counter loop looks like. Fine. They're easy to find. You do peel. What the hell's peel? Peel means you take the first iteration and you run it before the main one, because tests that are loop invariant will be run in the first iteration, the peeled iteration, and then because they've been run already, they'll never fail in the second main body, and you can get rid of them. Commonly, this will be null pointer checks for values you've never null pointer checked before, usually some array. So you peel an iteration, and all your null pointer checks happen in the peel version. The main body now has no null pointer checks, but it probably has range checks. So then you peel a body above and below called a pre-loop and a post-loop. The pre-loop is going to handle the edge cases where you might underflow, and the post-loop is going to handle edge cases where you might overflow. And they have a dance around path for if they're never taken at all, and they're a standard loop, but you don't do further optimization on the pre and the post. And then you remove the checks from the inner loop, the main one, and now you want to optimize with iter, but you force the pre and the post to stick around for a second here. And the main loop probably shrinks a whole lot, having no range checks and no null pointer checks. It becomes really small. And if it's really small, you're going to unroll it by power of 2 by simply doubling it. I make a copy of it, literally paste it in the code, make this copy, paste it after this copy, thread the control flow straight through, done. Throw it back at iter. Oh, there's a bunch of common stuff in there that folds up again. And for people doing sort of HPC style math, walking through big arrays, stencil calculations and the like, happens really easily, really quickly, and suddenly you get Fortran-like performance out of the thing. Every time I double the body, I have to handle only an even count of iterations. Here I'm handling them all, here I'm only handling an even count. Where's the odd iteration? If the loop tripped 5 times, and it was 1, 2, 3, 4, 5, and now it's 1, 2, 3, 4, where does the 5th iteration go? I put it in the post loop. So the post-loop trip count gets a little complicated. It says take the trip count for the loop and do the right kind of mod math on it, and that's your trip count for the post iteration. And it has a few range checks in it, but I don't care because the bulk of the iterations are going to be run in the main loop, which is going to be unrolled and have no other checks in it and carry all the load. So in the end, you end up with a funny thing of a pre-loop, which probably disappears after iter decides it can't ever execute, a post loop which has a couple odd iterations to take up the odd space, and a main body that's probably unrolled between 2 to 8 times, depending on how tight your loop was. It won't get too big or you have iCache blowout, but if you have a really dumbass, people write these micro benchmarks performance tests. If you have a really dumb one, it will just be unrolled sort of endlessly, and by powers of 2, and you'll have a logarithmic execution of the inner loop of 99.999% of your executions, and effectively your program will run in constant time independent of trip count because you wrote a dead micro benchmark. Fine. The different problem solved long ago, maybe. But typical, like just big array math turns into the same kind of code you get out of a C compiler. Checkcast, instance of array store, and also guarded inlining do a thing which I'm going to run out of time for, so go look at the paper. But is A an instance of a B? You look at the class hierarchy depth of B. It comes with a number. It's 2, 3, 4, 5 deep in the class hierarchy. You look that up in a fixed table based on the A. And if you find a match, you're an instance of, and if you don't, you're not. And it's a really cheap-ass test. Typically turns into a load compare branch, which is 1 clock on an x86. Heroic optimizations. Many safety checks just rarely fail, right? But if they do fail, they probably fail again and again, so there have to be something regionally done on them if they're going to fail. So this falls into the categories of range checks and most null checks and array store and yada, yada, yada. So I'm going to heroically assume the best. This test has never failed yet. Let's assume it's never going to fail. So I want a correctness test, and I'm going to go hard for the fast case. And the slow case, I have to have some sort of recovery on, so I'm going to cut it out to the interpreter. I'm going to deoptimize, more on that in a minute. And mostly this works really great, but occasionally it fails. And if it fails, I deopt in the interpreter, ouch. Now I have to unwind. So I have to take my compiled frame, which is inline, many Java frames or JVM bytecode frames, explode them out into the interpreter for every nested interpreter frame you need, and I have to set a bit somewhere that says I failed this heroic optimization. Now I'm going to run on in the interpreter, but reset all my counters to let it profile again. And after I've done profiling a little while, the JIT will trigger again. The JIT comes in and rejits, but not being quite so heroic second time around. It has to test that bit and say, this one might fail. It's failed before, so let's go ahead and put code. So like the zipper where I bailed off to the interpreter, now I'll put both arms of the zipper in. For instance, there are lots and lots of these. Hard part, tracking that heroic bits through multiple layers of inlining. If you don't get that right, you get in this endless deopt recompile cycle where you optimize, you execute, you hit the heroic fail, you deopt, you go to the interpreter, you reprofile, you go back to rejit, you miss the heroic bit because you set it in the wrong place. So you do the same heroic optimization, which fails the same way a second later, and you're endlessly compiling and deopting, compiling, deopting. We had a lot of these bugs before. It took a while to get most of these bugs out. Deopt, I mentioned it a bunch. What is it? It's the backup plan. As a philosophical compiler mindset, it's your recovery option for every failure. Just go back to the interpreter. Do not try to do everything in the compiler. I will definitely look at a TLab to do an allocation by a bump pointer, but if the TLab fails, I am not jitting code to do a GC. I'm just going to bail out, right? So, do what's hot, do what can be compiled, everything else, go to the interpreter. Right? If you're going to load a class for the first time, at the time I'm jitting the code, I'll see you haven't loaded this class yet. I cut you off as a check, and you go to the interpreter. If you hit that path, you go to the interpreter, who then loads the class necessary, and the rejits with the class now loaded. What is it? How is it implemented? You have to track the JVM state, the Java virtual machine architected state, which is this little stack machine that has pushes and pops. It's a stack machine. Something like an x86 track state. But an x86 does wide execution all the time, and under the hood, it's got these wild out of order, every kind of micro-op going on, and if an exception, an interrupt comes in, he rolls you back to some x86 state. Not every possible point can be interrupted. Same thing goes on here at safe points. If an exception comes in, you go to some safe point. Not every point in the Java code or the Java bytecodes will be a safe point and can be interrupted at. Right? So there's some places that you get interrupted at, and the compiler picks them and optimizes for the handful of places. But when he does it, the implementation is he has a mapping from the internal machine code registers and stack states and whatever bits to the JVM's architected state. And these safe points are not really related to GC. They are overloaded in the implementation. There's no need except for convenience. It's not a GC thing, but it's definitely a JIT thing. In particular, though, I still want to get good code out. So from the compiler's point of view, a safe point is just like a call instruction that reads all the variables that are visible, including all the memory effects, and it's very, very rarely taken. It's on some if branch that says if something horrible happened, do this function call that reads all possible state. That's all I need. I hand this off to the optimizer in that way, and the optimizer goes to town. So things are kept alive because there's these use-def edges to say I have to have this value, but there's a very low execution frequency branch involved where the code scheduler and the spill code do the right things. They push the spill code down in there, they push the cleanup execution bits down in these off branches. Things that are needed for the interpreter but not the JITted code get spilled to the stack and never looked at again unless you deoptimize. So you get a great fast path, but you get a full unwind. You can run your debugger and stop at any point, apparently to you, any point. What really happens, of course, you stop at some prior safe point, and then you get in the interpreter and you step forward one by one to the bytecode you're interested in. But from the outside, it looks like you can breakpoint at any point and still run at C code speeds. Okay, a little bit about some debugging hints. So C2 is a giant monster to go debug. You have the case where the common cases are fast and run well and have been well debugged, and you have something rare happens and it's complicated, so the bug lurks there. How do you find it? So the way that it's done it was done at the time I was there was you use these blah, blah, blah lot flags. What's blah, blah, blah? It's compile a lot, deoptimize a lot, safe point a lot, GC a lot. There's like 20 of them. There's a lot flags. And they force the rare case to be common, which means you're slow. So you get a weekend QA run, but you probably find your bug sort of directly. After that, there's binary search using CI start and stop. Bunch of other flags for gating, inlining, breaking on certain things getting inlined or called or whatever. There's lots of options for choosing what to compile when you have thousands of things compiling in a large, busy web server before the crash happens. So, I'm going to wrap it up. Sea of nodes. It's the IR in HotSpot. It's all program semantics with nodes and edges, where the nodes are tiny and the edges are raw pointers, done for speed purposes, compilation speed. On this graph IR, graph rewrite rules rule. Most of your optimizations come from peepholes, which are themselves sort of trivially, locally correct. I just look at the nearby neighbors and make a transformation based on them. Typing system defines what a compiler can talk about and reason about, and includes, unfortunately, a lot of heavy-duty theory. I encourage you to look at the Wikipedia page, but you can read in there's building using hash cons is, if you don't know what that is, go understand it. Before you start mucking around in the type system, it's easy to get it wrong, and if you get it wrong even a little bit, you'll get it wrong in a bad way and things won't work. But you get it right, it's fast and it's cheap and accurate and precise, has the right things. There's a lot of Java-specific optimizations that these days are done by other things such as JavaScript, but at that time were brand new. This notion of fast path, slow path with heroically deopt on the slow path. Null check unzipping is one of many things that we do to track null pointers and get rid of null pointers. Range check elimination, subtype checks, class hierarchy analysis. Aggressive inlining, perhaps done too early, made up for by an expensive register allocator that is tolerant of over-inlining. And, you know, it has withstood the test of time. I walked away a long, long time ago from it, from at least the Oracle version of things. Typical optimizing compiler lifetime is 20-odd years. So there's a lot of cruft in there, but the bones, the core of it remain. And it remains fairly simple. If you understand the graph and you understand the types, you got 90% of what you need to know to make the compiler do things. For me, it was a labor of love, and I hope you enjoy hacking it too. And that's the end.
Thank you, Cliff. Thank you, Cliff. We have time just for one question. So if you have one, please raise your hand up. Okay.
Hi, Cliff. So you didn't mention escape analysis. Haven't you thought about that?
I did it at Azul, which didn't make it over to Oracle, so I don't know what Oracle has done. I didn't talk about memory because, as you see, I touched a lot of things with one slide each, and I ran out of time. The whole what you do with memory is its own, hour-long discussion. So I have thought about it a bunch. I did a lot of that work at Azul Systems, including the kind of escape analysis you need for like Scala was in the Azul version of C2. Yes. So given the time constraints, I will be available for conversations for a while, and then at some point we'll break for lunch. But I guess we go to a meeting area, and we can go in depth on a lot of things, including escape analysis.
Maybe someone else?
Up front?
Okay.
In the back. Okay.
No?
Yes, up front. What?
Okay.
Can you quickly outline how you, the architecture description files and how in general you made a compiler suitable for many platforms all at once, so like the backend?
Okay, how to do the, yeah, okay, fine. So there are some things there that I wouldn't do again, including the Burj technology. There is an architecture file that is used to describe a CPU architecture, including the kind of instructions and a mapping from the C2 ideal nodes to machine equivalents, and the registers that are allowed, and the encodings for the machine code encodings for them is sort of the common set of things. There's a bunch of other things that are in there that are all these fine-grained details, but the big pieces are, here's a mapping from idealized nodes, which is what the IR mostly runs on until you get onto CodeGen, to hardware instructions. And the registers that are allowed, both on each individual hardware instruction input and overall what are the set of registers that are allowed in the system. And there is a tool which reads this file, which is in a funny, its own little format, and spits out C code that is then compiled in with the rest of the system, builds what's called a BERS pattern matching, which does optimal, for some definition of optimal, mapping of hardware instructions to ideal nodes by doing like an overlapping tree, like usually a hardware node covers 2 to 5 ideal nodes, and so there's some tiling operation that covers them all, including if it ate this region, then those edges in between don't have to be register allocated, but all the edges on the outside do, and then what are the registers that are involved. And the registers turn into basically a bit set for every input and output of allowed registers, and the register allocator groks that bit set and uses it to pick the right registers. So that gets into register allocation pretty heavily right away, because that's how you describe the inputs to the register allocator. After that, I'm going to claim, sit down with a piece of paper and the source code, and we can start working through the details, but that's a lot of nitty-gritty for this talk.